Bihar Engineering University, Patna. Concrete Technology. B.Tech 7th Sem Examination PYQ 2023. Question 2. Describe the air-entraining cement and sulfate-resisting cement. Answers: air-entraining cement. Air-entraining cement is a type of cement that contains additives that introduce tiny air bubbles into the concrete mix. These bubbles help improve the workability, durability, and resistance to freeze-thaw cycles. The air-entraining agents, such as resins, fats, or fatty acids, act as surface active agents that create a stable network of microscopic air pockets. Advantages of air-entraining cement: 1. Improved workability, enhances the plasticity and cohesion of the concrete mix. 2. Increased durability, provides better resistance to freezing and thawing in cold climates. 3. Reduced bleeding and segregation, enhances the uniformity of the concrete mix. 4. Lower water demand, reduces the amount of water required for a workable mix. Applications: used in areas exposed to severe freezing and thawing conditions. Suitable for road pavements, bridges, and hydraulic structures. Sulfate-resisting cement. Sulfate-resisting cement is a type of cement specially designed to resist the attack of sulfates present in soil and water. It has a lower content of tricalcium aluminate, which reduces the formation of expansive compounds when exposed to sulfates. Advantages of sulfate-resisting cement: 1. High sulfate resistance, prevents deterioration caused by sulfate attack. 2. Increased durability, enhances the lifespan of concrete structures in aggressive environments. 1. 2. 3. Lower heat of hydration, reduces the risk of thermal cracks in mass concrete structures. Applications: used in foundations and basements exposed to sulfate-rich soil. Suitable for marine structures, sewage treatment plants, and industrial facilities. Ideal for structures in contact with groundwater containing sulfates. Question 2. Differentiate between artificial sand and natural sand. Answers: difference between artificial sand and natural sand. Feature: artificial sand, natural sand. Source: manufactured by crushing rocks, stones, or aggregates. Obtained naturally from riverbeds, seashores, and pits. Shape: cubical or angular in shape, providing better bonding in concrete. Rounded and smooth, leading to weaker bonding. Grading: can be controlled during manufacturing to meet specifications. Varies naturally, requiring sieving and washing. Impurities: free from organic impurities, silt, and clay. May contain clay, silt, and organic matter, reducing strength. Strength: provides higher compressive strength due to angular shape. Slightly lower strength compared to artificial sand. Availability: can be produced as needed, ensuring a consistent supply. Limited availability due to environmental regulations. Cost: usually more expensive due to manufacturing and processing. Generally cheaper but depends on location and availability. Environmental impact: sustainable as it reduces dependence on natural riverbeds. Over-extraction leads to environmental degradation and erosion. Usage: used in high-strength concrete, plastering, and construction. Commonly used in regular concrete, masonry, and filling. Conclusion: 3. Artificial sand is preferred for its strength, controlled quality, and sustainability. Natural sand is traditional but may not always be environmentally or structurally ideal. Question 3. What is alkali-aggregate reaction? What are the factors which affects this reaction? How can this reaction be controlled? Answers: alkali-aggregate reaction. Alkali-aggregate reaction is a chemical reaction between the alkalis present in cement and reactive silica in aggregates. This reaction forms an expansive gel that absorbs water and swells, leading to cracking and deterioration of concrete over time. Types of alkali-aggregate reactions. 1. Alkali-silica reaction, the most common type, occurring between alkalis and reactive silica in aggregates. 2. Alkali-carbonate reaction, a less common reaction between alkalis and certain carbonate rocks, leading to expansion and cracking. Factors affecting alkali-aggregate reaction. 1. Alkali content in cement. Higher alkali content increases the risk of AAR. Limiting alkali content in cement can reduce the reaction. 2. Presence of reactive silica in aggregates. Some types of aggregates contain reactive silica, which reacts with alkalis. 3. Moisture availability. Water is essential for the reaction to occur. Dry conditions prevent the formation of the expansive gel. 4. Temperature conditions. High temperatures accelerate the reaction and expansion, worsening the damage. 5. Cement content in concrete. Higher cement content increases alkali concentration, promoting AAR. 4. 6. Supplementary cementitious materials. Materials like fly ash, silica fume, and slag can help reduce AAR by consuming excess alkalis. 7. Time duration. AAR progresses slowly over years, leading to long-term durability issues in structures. Effects of alkali-aggregate reaction, expansion and cracking in concrete. Loss of structural integrity and durability. Reduced service life of concrete structures. Control measures for alkali-aggregate reaction. To prevent or minimize alkali-aggregate reaction, the following measures can be implemented. 1. Use of low-alkali cement. Use cement with alkali content below 0.6% to reduce the availability of alkalis. Low-alkali cement helps minimize the reaction with reactive aggregates. 2. Use of supplementary cementitious materials. SCMs reduce alkali concentration and limit silica reactivity. Common SCMs used to mitigate AAR. Fly ash reduces alkali content and binds reactive silica. Silica fume reacts with alkalis before aggregates do. Ground granulated blast furnace slag lowers permeability and reduces reaction rate. Metakaolin helps in reducing expansion due to AAR. 3. Use of non-reactive aggregates. 5. Conduct petrographic analysis to check aggregate reactivity. Select aggregates that have low silica reactivity. Avoid using aggregates known to cause AAR. 4. Limit moisture availability. Reduce permeability of concrete to prevent water ingress. Apply sealants, coatings, or waterproofing materials to minimize moisture absorption. Improve drainage around structures to prevent water accumulation. 5. Use of lithium-based admixtures. Lithium compounds can suppress the formation of expansive gels. Used as a chemical treatment to mitigate AAR effects. 6. Proper mix design and quality control. Maintain a well-controlled water-to-cement ratio to reduce permeability. Use proper curing methods to avoid excessive moisture exposure. Follow standardized testing procedures for aggregate selection. Question 3. Define the soundness of cement. Describe the method of determination of soundness of cement. Answers: soundness of cement. Soundness of cement refers to its ability to retain its volume after setting without undergoing excessive expansion. If cement is unsound, it can cause cracks and structural failure over time. Unsoundness is usually caused by excessive free lime magnesium oxide sulfates. 6. These compounds can expand after hydration, leading to delayed expansion and cracking in concrete. Method for determination of soundness of cement. The soundness of cement is tested using the Le-Chatelier test and the autoclave test. 1 Le-Chatelier test apparatus required. Le-Chatelier apparatus glass plate weighing balance water bath procedure. 1. Prepare cement paste. Mix 100 g of cement with 0.78 times its weight of water to form a paste. 2. Fill the Le-Chatelier mold. Place the cement paste inside the mold and cover it with a glass plate. 3. Initial curing. Submerge the mold in water at 27 degrees Celsius for 24 hours. 4. Boiling in water. Transfer the sample to boiling water for 3 hours to accelerate expansion. 5. Measure expansion. Measure the distance between the indicator arms before and after boiling. The expansion should not exceed 10 mm. 2. Autoclave test procedure. 1. Prepare a cement paste and shape it into bars of 25 x 25 x 250 mm. 2. Cure the specimen in normal water for 24 hours. 7. 3. Place the specimen inside an autoclave at 2.1 MPa pressure and 215 degrees Celsius temperature for 3 hours. 4. Measure the expansion after cooling. The permissible expansion limit is 0.8%. Question 4. Describe the various causes of deterioration of concrete. Answers. Causes of deterioration of concrete. Concrete deterioration occurs due to various physical, chemical, and environmental factors, leading to reduced strength, durability, and service life of structures. The major causes of deterioration are: 1. Physical causes. A. Freeze-thaw cycles. In cold regions, water inside concrete pores freezes and expands, causing internal pressure. Leads to cracking, scaling, and spalling of concrete. B. Thermal stresses. Temperature variations cause expansion and contraction, leading to cracks. High temperatures can cause loss of moisture and reduce strength. C. Abrasion and erosion. Continuous traffic, machinery, or flowing water wears down the surface. Common in pavements, bridges, and hydraulic structures. D. Shrinkage. Cracks. Plastic shrinkage. Drying shrinkage. 2. Chemical causes. A. Alkali-aggregate reaction. Alkalis in cement react with silica and aggregates, forming an expansive gel. Leads to cracking and reduced strength. B. Sulphate attack. 8. Sulfates from soil or water react with tricalcium aluminate in cement. Causes expansion, cracking, and loss of bond strength. C. Carbonation. Atmospheric CO2 reacts with calcium hydroxide 2, in concrete. Lowers pH, leading to corrosion of steel reinforcement. D. Chloride attack. Chlorides penetrate concrete. Leads to corrosion of steel reinforcement and reduces durability. 3. Structural and construction-related causes. A. Poor workmanship. Inadequate mixing, curing, or compaction results in weak concrete. Poor construction joints create weak zones. B. Overloading and structural deficiencies. Load beyond design capacity causes cracking and deformation. Poor reinforcement design leads to structural failure. C. Corrosion of reinforcement due to chlorides, carbonation, or poor concrete cover. Corroded steel expands, causing cracks and spalling. 4. Environmental causes. A. Pollution and acid rain. Industrial gases cause acidic reactions with concrete. Leads to surface deterioration and loss of strength. B. Marine environment. Exposure to seawater leads to chloride attack, sulfate attack, and erosion. Common in harbors, bridges, and coastal structures. C. Biological growth. Algae, fungi, and moss grow in damp conditions, reducing concrete durability. 9. Question 4. Write down the various stages of concrete production. Describe any two. Answers. Stages of concrete production. Concrete production involves several stages to ensure quality, strength, and durability. The major stages are 1. Batching 2. Mixing 3. Transportation 4. Placing 5. Compaction 6. Curing 7. Finishing 8. Quality control. 1. Batching. Batching is the process of measuring cement, aggregates, water, and admixtures in accurate proportions to achieve the desired concrete strength and workability. Types of batching. Volume batching. Materials are measured by volume using boxes or containers. Weight batching. Materials are measured by weight using weigh batchers. Importance. Ensures correct mix proportions. Improves concrete quality and consistency. 2. Mixing. Mixing ensures that cement, aggregates, water, and admixtures are evenly distributed to form a homogeneous concrete mix. Types of mixing. Hand mixing, done manually for small projects, but less uniform. Machine mixing, done using concrete mixers for better consistency. Ready mix concrete, prepared in a batching plant and transported to the site. Importance. Ensures uniform distribution of materials. Improves workability and strength of concrete. Question 5. Define water-cement ratio and gel space ratio. How does water-cement ratio influence concrete strength? Answers. Water-cement ratio. The water-cement ratio is the ratio of the mass of water to the mass of cement used in the concrete mix. It is a crucial factor in determining the strength, durability, and workability of the concrete. The formula for the water-cement ratio is =/ A lower water-cement ratio results in higher strength and durability, as it leads to a denser and more impermeable concrete mix. Conversely, a higher water-cement ratio results in weaker and more porous concrete. Gel space ratio. The gel space ratio refers to the ratio of the volume of hydration products to the volume of pore spaces in the hardened concrete. The gel refers to the solid products formed from the chemical reaction between cement and water, while the space refers to the voids that remain in the concrete matrix. A higher gel space ratio indicates better hydration and denser concrete with fewer voids, which typically leads to stronger and more durable concrete. =/ Influence of water-cement ratio on concrete strength. The water-cement ratio has a significant influence on the strength of concrete. When the water-cement ratio is low, there is less water available for hydration, resulting in a denser concrete with fewer pores and a higher strength. However, if the water-cement ratio is too low, the mix becomes difficult to work with and may not fully hydrate, which can result in reduced strength. On the other hand, if the water-cement ratio is high, excess water leads to the formation of large voids within the concrete, which decreases the overall strength and durability. 10. Therefore, an optimal water-cement ratio is essential for balancing strength, workability, and durability of concrete. In summary, lower water-cement ratio equals stronger concrete. Higher water-cement ratio equals weaker concrete. Question 6. Define the concrete cracking. What are the types of cracks? Enlist the causes concrete to crack. Describe any 4 causes in details along with the remedial measures to prevent them. Answers. Concrete cracking. Concrete cracking refers to the formation of visible fractures or fissures in the concrete structure due to the internal stresses, environmental factors, or improper construction practices. Cracks in concrete can affect the strength, durability, and aesthetics of the structure. Cracking is a common phenomenon, but if not addressed properly, it can lead to significant damage. Types of concrete cracks. 1. Plastic shrinkage cracks occur during the curing process when the surface of the concrete dries out too quickly, causing the top layer to shrink while the inner layers are still moist. 2. Shrinkage cracks. These occur over time as the concrete continues to lose moisture and shrinks. This is more prominent in structures where the concrete is not properly cured. 3. Settlement cracks. These happen when the concrete settles unevenly, which may be due to insufficient compaction, unstable soil, or a lack of adequate support during the curing process. 4. Thermal cracks. These occur when the concrete experiences significant temperature variations, causing it to expand and contract. This can be caused by rapid temperature changes in hot or cold environments. 5. Expansion cracks, caused by the expansion of concrete, often due to moisture absorption or chemical reactions. 6. Structural cracks. These cracks are due to structural issues such as overloading, incorrect reinforcement design, or poor workmanship. Causes of concrete cracking. 1. Excessive water-cement ratio. 11. Cause. Using too much water in the mix increases the porosity of concrete, leading to shrinkage cracks as the concrete dries and the excess water evaporates. Remedial measures. Reduce the water-cement ratio to ensure a denser concrete mix. Use admixtures to improve workability without increasing the water content. 2. Drying shrinkage. Cause. When concrete dries too quickly, especially in hot or windy conditions, the surface contracts faster than the interior, leading to cracks. Poor curing practices exacerbate this problem. Remedial measures. Proper curing techniques, such as keeping the concrete surface moist for an extended period, can help prevent drying shrinkage cracks. Additionally, using retarders or curing compounds can reduce water loss from the concrete surface. 3. Thermal expansion and contraction. Cause. Concrete expands when it is hot and contracts when it cools. If temperature fluctuations are severe, it can lead to thermal cracking. This is especially true for large concrete slabs or structures with significant surface area exposed to the sun. Remedial measures. Control the curing temperature, avoid large temperature differences between day and night, and introduce expansion joints in concrete slabs and structures to allow for movement. 4. Improper reinforcement. Cause. Insufficient or poorly placed reinforcement in the concrete can lead to cracks when the concrete is subjected to tensile forces. Concrete is strong in compression but weak in tension, so without adequate reinforcement, it may crack. Remedial measures. Ensure that the correct amount and type of reinforcement is used in the right locations according to design specifications. Proper placement and adequate concrete cover over reinforcement can prevent cracking. 5. Chemical reactions. Cause. A chemical reaction between the alkalis in cement and the silica in aggregates can cause expansion, leading to cracking over time. Remedial measures. Use non-reactive aggregates, or add pozzolanic materials such as fly ash or slag to the concrete mix to prevent the alkali-silica reaction. 6. Overloading. 12. Cause. Applying more load to the concrete structure than it was designed to carry can cause the concrete to crack under stress, often leading to structural failure. Remedial measures. Ensure that the concrete mix design is appropriate for the anticipated loads. Regular inspections and load testing can also help prevent overloading. Question 7. Define the quality control of concrete. Describe the process of quality control from the procurement of the ingredients of concrete to the finishing stage concrete structural component. Answers. Quality control of concrete. Quality control of concrete is a systematic process aimed at ensuring that the concrete used in construction meets the required specifications and standards for strength, durability, and performance. The main goal of quality control is to prevent defects, minimize variations in the properties of concrete, and ensure that the finished structure performs well under the intended service conditions. Process of quality control from procurement to finishing stage. 1. Procurement of ingredients. The quality of the raw materials is critical for ensuring the overall quality of concrete. The quality control process begins at the procurement stage and includes cement. Ensure that the cement used complies with the relevant standards. The cement should be stored properly to prevent moisture absorption. O aggregates. The quality of aggregates is crucial for achieving the desired strength and durability. Aggregates should be clean, free from impurities, and conform to the required size gradation as per standards. O water. Water should be clean, potable, and free from contaminants like salts, oils, and organic matter. The water used must be tested for chemical composition, as impurities can affect the hydration process and the quality of concrete. O admixtures. Admixtures are used to modify the properties of concrete. Their quality must be tested to ensure that they are compatible with the mix design and meet the required standards. 2. Mix design. 13. O process. The mix design determines the correct proportion of materials to achieve the desired strength, workability, and durability of concrete. A concrete mix design is based on the desired properties and performance requirements of the structure, such as compressive strength, durability, and environmental exposure. O quality control. The mix should be tested in the laboratory to ensure that it achieves the target strength. This involves preparing trial mixes and performing tests like compressive strength tests on cubes or cylinders at specified curing ages. 3. Batching and mixing. O process. Once the ingredients are procured and the mix design is finalized, the batching process begins. Accurate measurement of ingredients is essential to ensure consistency in the concrete mix. Batching can be done by weight or by volume, with weight batching being the more accurate method. Mixing is done in a concrete mixer to ensure uniform distribution of all ingredients. O quality control. Batching equipment must be calibrated regularly to ensure correct measurements of materials. The concrete mixer should be in good working condition, and the mixing time must be adequate to ensure uniformity. Samples should be taken for testing to confirm the consistency and workability of the concrete. 4. Transportation and placing. O process. Once mixed, the concrete is transported to the construction site. The concrete should be delivered without segregation or loss of workability. During transportation, precautions should be taken to avoid delays that may cause initial setting. O quality control. During transportation, the time taken should be minimized, and concrete should be placed as soon as possible. The use of transit mixers ensures uniformity during transit. The concrete should be placed within the specified time limits to avoid premature setting and to maintain workability. 5. Compaction. O process. After placing the concrete, it is compacted to remove air voids and ensure that the mix fills all spaces within the formwork. Compaction is done using vibrators or manual tamping methods. O quality control. Proper compaction is necessary to achieve dense and uniform concrete. Insufficient compaction can lead to honeycombing, voids, and reduced strength. The frequency and technique of compaction should be monitored and controlled to avoid over or under compaction. 14. Question 8. Explain the significance of non-destructive tests. Describe the ultra-pulse velocity test used in monitoring of concrete structures. Answers. Significance of non-destructive tests in concrete structures. Non-destructive testing refers to a range of testing methods used to evaluate the properties and integrity of concrete structures without causing any damage to the material. The significance of NDT lies in its ability to monitor, assess, and detect potential issues in concrete without compromising its strength or functionality. Some key benefits of NDT include: 1. Cost-effective and time-saving. NDT methods can identify problems early on, potentially preventing costly repairs or replacements. They also save time compared to more invasive testing methods. 2. Safety. NDT methods help assess the structural integrity of concrete, ensuring that buildings, bridges, and other structures are safe for use and comply with regulations. 3. Assessing concrete condition. NDT is used to evaluate the strength, uniformity, homogeneity, and durability of concrete without disrupting its operation or use. 4. Monitoring over time. NDT allows for continuous monitoring of concrete structures over time, helping detect deterioration due to aging, environmental factors, or external loads. 5. Non-invasive. These tests do not require sample extraction or causing damage, which is essential for maintaining the structure's serviceability. Ultra-pulse velocity test for monitoring concrete structures. The ultrasonic pulse velocity test is a popular non-destructive testing method used to assess the quality and integrity of concrete structures. It measures the velocity of an ultrasonic pulse passing through the concrete, which provides information about the material's uniformity, density, and the presence of cracks or voids. The test is based on the principle that the velocity of the ultrasonic pulse depends on the characteristics of the medium it passes through, such as density, elasticity, and homogeneity. Working principle of UPV. 1. Ultrasonic pulse. The test involves transmitting an ultrasonic pulse through the concrete using a transducer. The pulse travels through the concrete and is received by another transducer placed at a distance. 2. Pulse velocity measurement. The time it takes for the ultrasonic pulse to travel from the transmitter to the receiver is measured. The velocity of the pulse depends on the concrete's characteristics. The faster the pulse travels, the denser and more homogeneous the concrete is. 3. Pulse travel time calculation. The velocity is calculated using the formula 15 = where OV is the velocity of the ultrasonic pulse, OL is the distance between the two transducers, OT is the time taken for the pulse to travel. For evaluation of concrete quality, the velocity value is then compared to standard values or reference data to assess the quality of the concrete. Higher velocity typically indicates denser, stronger, and less porous concrete, while a lower velocity may indicate poor quality, cracks, voids, or other defects. Applications of UPV in concrete structures. 1. Detection of cracks and voids. UPV can detect internal cracks, voids, or honeycombing in concrete that are not visible on the surface. These defects may indicate weaknesses in the concrete structure. 2. Assessing concrete strength. By comparing the ultrasonic pulse velocity to known standards, the test can provide an indirect estimate of the concrete's compressive strength. This is particularly useful in evaluating the quality of concrete in existing structures where core sampling is difficult. 3. Evaluating uniformity. The UPV test can assess the uniformity of the concrete in a structure. Inconsistent pulse velocities in different areas of the structure may indicate variations in the concrete mix or improper curing. For monitoring concrete aging, UPV is useful in monitoring the condition of concrete over time. It helps assess how the material is aging and if any deterioration, such as cracking, has occurred due to environmental exposure or other factors. Procedure for UPV testing. 1. Preparation. Clean the surface of the concrete where the probes will be attached. The surface should be smooth and free from dirt or debris to ensure accurate readings. 2. Transducer placement. Place the transmitter and receiver transducers on opposite sides of the concrete structure. The transducers are usually coupled with a gel or water to improve the transmission of ultrasonic pulses. 3. Measurement. The ultrasonic pulse is transmitted through the concrete, and the time taken to travel through the material is recorded. For analysis, based on the pulse velocity, the quality of the concrete is assessed. A high velocity suggests good quality concrete, while a lower velocity may indicate potential problems. Interpretation of results. 16. High pulse velocity indicates that the concrete is of good quality, dense, and homogeneous with no significant cracks or voids. Moderate pulse velocity suggests that the concrete quality is average. There may be some surface defects or minor cracks, but the overall structure is still sound. Low pulse velocity indicates poor quality concrete, possibly due to the presence of cracks, voids, or honeycombing. It may also suggest deterioration of concrete over time. Advantages of UPV testing. 1. Non-destructive, no need to drill or extract samples from the concrete, preserving the integrity of the structure. 2. Quick and efficient, the test is fast and can be performed in situ, saving both time and money. 3. Portable, the equipment used for UPV testing is portable, making it suitable for field inspections and assessments. For early detection of issues, it helps detect issues such as cracking, voids, and other irregularities at an early stage, allowing for timely intervention. Limitations of UPV testing. 1. Surface preparation, the concrete surface must be clean and smooth for accurate results. 2. Limited information, while the UPV test can detect anomalies like cracks or voids, it cannot provide detailed information about the exact cause or location of defects. 3. Need for reference data, the interpretation of pulse velocity requires comparison with standard reference values or known characteristics of the concrete mix. Question 9. Write short notes on any 4 of the following: grouting, fineness, modulus of aggregates, hydration of cement, bulking of sand, polymer, concrete, slump test. 17. Answers: grouting. Grouting is a process of injecting a fluid material into voids or cracks in concrete or masonry structures to fill spaces, improve strength, and prevent water ingress. Grouting can be used to repair damaged structures, stabilize soil around foundations, and improve the bonding between different materials. Types of grouting. 1. Cement grouting, used to fill cracks and voids in concrete or masonry and to stabilize foundations. 2. Chemical grouting, involves injecting chemicals that react with moisture to form a solid mass, often used in soil stabilization. 3. Epoxy grouting, used for repairing cracked or damaged concrete surfaces to restore their structural integrity. Grouting enhances the strength, durability, and waterproofing properties of structures. Fineness modulus of aggregates. The fineness modulus is a numerical value that represents the average size of the particles in an aggregate sample. It is calculated by adding the cumulative percentages of the aggregate that pass through various standard sieves and dividing the sum by 100. The formula: a lower FM indicates finer aggregates. Fineness modulus is important in mix design, as it affects the workability and strength of concrete. Hydration of cement. Hydration of cement refers to the chemical reaction between cement and water that leads to the hardening of concrete. When water is added to cement, various compounds in the cement react with the water to form calcium silicate hydrate and calcium hydroxide 2, which give concrete its strength and durability. The main stages of hydration. 18. 19. 1. Initial setting, the cement starts reacting with water, and the mixture begins to stiffen. 2. Final setting, the reaction proceeds further, and the cement hardens completely. 3. Long-term hydration, the reaction continues slowly over months or years, strengthening the concrete over time. Proper hydration is critical for achieving the desired properties of concrete, such as strength and durability. Bulking of sand. Bulking of sand is the phenomenon where the volume of sand increases due to the presence of moisture. When water is added to dry sand, the moisture causes the sand particles to stick together, creating air pockets and increasing the overall volume. This is important to consider when measuring sand for concrete mix, as bulking can result in an incorrect proportion of materials. Factors affecting bulking: moisture content. Higher moisture content increases bulking. Type of sand: coarse sand tends to have less bulking compared to fine sand. To avoid errors in mix proportions, the bulking effect of sand should be accounted for when mixing concrete, especially in dry conditions. Polymer concrete. Polymer concrete is a type of concrete where polymer resins are used as a binding agent. The polymer binds the aggregates together, resulting in a concrete that has higher strength, durability, and resistance to chemicals, compared to conventional cement-based concrete. Types of polymer concrete. 1. Polymer modified concrete, regular concrete mixed with a polymer additive to improve certain properties. 2. Pure polymer concrete, concrete made entirely from polymer resin and aggregates, without cement. Benefits of polymer concrete: enhanced chemical resistance, improved resistance to cracking, higher compressive and tensile strength. 20. Reduced porosity, making it more water resistant. Polymer concrete is often used in applications where traditional concrete would not perform well, such as in highly corrosive environments. Slump test. The slump test is a measure of the workability or consistency of freshly mixed concrete. It is conducted by filling a conical mold with concrete and then removing the mold. The slump is the difference between the height of the mold and the height of the concrete after the mold is removed. Procedure: 1. Place the cone on a flat surface and fill it with concrete in layers. 2. Compact each layer with a tamping rod. 3. Lift the cone vertically, and measure the slump by calculating how much the concrete has settled. Interpretation of results. High slump indicates a wetter, more workable mix. Low slump indicates a stiffer mix with less workability. The slump test is commonly used to ensure that concrete mixes are consistent and that the concrete has the required workability for placement and compaction. These short notes provide a quick overview of each topic, and they can be expanded with more detailed information as required.